On August 17th, 2017, two dead stars collided. They were neutron stars. Each one was a collapsed core of a once massive star, packing more mass than our sun into a sphere just a few miles across. They had been orbiting each other for eons in a galaxy named NGC 4993, about 130 million light years from Earth. Their final dance was a death spiral. As they got closer, they spun faster and faster, whipping space and time into a frenzy. On Earth, two sets of detectors, LIGO in the United States and Virgo in Italy, felt the faintest tremor from this event. It was a ripple in spacetime itself, a gravitational wave. The signal, named GW170817, lasted for about 100 seconds. It told us a story of cosmic violence. Just 1.7 seconds after the gravitational wave arrived, telescopes saw a burst of gamma rays from the same patch of sky. For the first time, we had seen and heard the same cosmic event. The collision created a kilonova. It was an explosion that forged an immense amount of heavy elements. Scientists estimate that the crash produced around 16,000 times the Earth's mass in heavy elements. This included about 10 Earth masses of pure gold and 50 Earth masses of platinum. The gold on your finger might have been born in a collision just like this. This event was a triumph. It confirmed so many things we thought we knew about the universe, but it also threw a spotlight on the things we don't understand at all. A neutron star is one of the densest things in the universe, but it is nothing compared to a black hole. And the collision of two 1.5 solar mass objects is a firecracker compared to the mysteries at the heart of every large galaxy. There, we find supermassive black holes. These are not a few times the mass of the sun. They are millions, or even billions, of times the mass of the sun. The neutron star collision helps us understand how a few solar masses of matter behave. But it does not tell us how you build a monster a billion times heavier, especially in the early days of the universe. We see these giants fully formed when the universe was less than 1 billion years old. That is not enough time, according to our old theories. It is a cosmic deadline that seems impossible to meet. So how did they get there? The truth is, nobody knows for sure. There is no single agreed-upon answer. Instead, there are ideas, lots of them. They range from the straightforward to the truly bizarre. Each one tries to solve the problem of getting very big very fast. Number 19, the black holes are made of something else entirely. The universe may contain particles that form a Bose-Einstein condensate, a strange state of matter where particles act as a single quantum entity. Some dark matter candidates, like axions, could theoretically form such a condensate. A black hole formed from this material would have different properties than one formed from normal matter. For instance, the M-sigma relation, the tight correlation between a supermassive black hole's mass and the velocity dispersion of its host galaxy's bulge, might be explained if both the black hole and the galaxy bulge formed from the same underlying dark matter structure. This idea would also mean that supermassive black holes could form without any stars at all. What if the monsters at the center of galaxies are not made of the same stuff as us? The standard picture is that black holes are formed from collapsed normal matter. That is baryons, the family of particles that includes protons and neutrons, but the universe is mostly not baryonic. About 85% of the matter out there is dark matter. We know it is there because we see its gravity. It holds galaxies and galaxy clusters together, but we have never detected a dark matter particle directly. We do not know what it is. One theory suggests supermassive black holes are not made of baryonic matter at all. Instead, they could be giant, dense cores of dark matter. Some models of dark matter propose particles called bosons. Unlike fermions, the category that includes electrons and protons, bosons can't occupy the same quantum state. Under extreme cold and density, they can form a state of matter called a Bose-Einstein condensate. The entire collection of particles acts like a single giant wave. It has been created in labs on Earth, with atoms like rubidium at temperatures just billionths of a degree above absolute zero. The idea is that in the early universe, dark matter bosons could have collapsed under their own gravity to form these condensates. These objects would be called boson stars. They would be compact, massive, and completely invisible, just like a black hole. If a boson star gets massive enough, it would eventually collapse into a true black hole with an event horizon. But even before that, it could be massive enough to act as the gravitational anchor for a young galaxy. This theory offers a neat way around the timing problem. You do not need to wait for stars to form, die, and then slowly merge and accrete. The dark matter is already there from the very beginning. It can start collapsing into these massive objects almost immediately after the Big Bang. The dark matter halos that we know surround galaxies would naturally have a dense core. Perhaps that core is a giant boson star or a black hole that used to be one. This idea is highly speculative. It depends on dark matter being a specific type of particle, a light boson, that we have not discovered. Actions are a popular candidate. They are hypothetical particles proposed to solve a problem in particle physics, but they also happen to be a good candidate for cold dark matter. If supermassive black holes are made of axions or other bosons, they might behave slightly differently than their baryonic cousins. For example, they might not spin the same way. The gravitational waves from mergers of such black holes could carry a distinct signature, a way to tell what they are made of. This would be a profound discovery. It would mean the objects we have been studying at the centers of galaxies are not just the end state of stars, but a window into the nature of dark matter itself. It connects the largest structures in the cosmos to the smallest, most fundamental particles. The challenge is finding proof. We would need to detect a dark matter particle in an experiment on Earth, or find astronomical evidence that is impossible to explain with normal black holes. The James Webb Space Telescope is looking for the earliest galaxies. If it finds massive central objects in galaxies that have not had time to form many stars, that could be a clue. It might point to a formation mechanism that bypasses stars altogether. It might point to dark matter. Number 18, cosmic strings may have seeded the universe with black holes. Cosmic strings are not the same as the strings in string theory. They are hypothetical one-dimensional defects in the fabric of space-time, possibly formed during phase transitions in the very early universe. A loop of cosmic string could be incredibly dense, and if it collapsed, it could form a black hole without any stellar precursor. The mass of the black hole would depend on the size of the loop. This process could have created a wide range of black hole masses, including seeds massive enough to grow into the supermassive black holes we see today. The Laser Interferometer Space Antenna LISA, a future space-based gravitational wave observatory, may be able to detect the gravitational waves from oscillating cosmic string loops, providing evidence for their existence. Let us consider an even more exotic idea. What if black holes were not seeded by stars or gas clouds or dark matter clumps, but by defects in space-time itself? This brings us to the concept of cosmic strings. These are not the tiny strings of string theory. They are theoretical objects thought to be incredibly long, thin filaments of pure energy. They are a type of topological defect. Imagine what happens when water freezes into ice. When crystals form in different places and grow outwards, where these different crystal regions meet, they do not always line up perfectly. This creates cracks and imperfections in the ice. A similar thing may have happened in the first fraction of a second after the Big Bang. As the universe cooled, it went through a series of phase transitions similar to water freezing. These transitions may not have happened perfectly uniformly everywhere, where different regions of the new, cooler phase of the universe met, defects could have been left behind. Cosmic strings would be one-dimensional or line-like defects. They would be thinner than a proton but could stretch across vast cosmic distances. They would also be unbelievably dense. A piece of cosmic string just a mile long could have more mass than the Earth. The theory goes that these strings would whip through space at nearly the speed of light. Sometimes a string might intersect itself, forming a closed loop. These loops would oscillate violently, radiating away their energy as gravitational waves. As a loop radiates energy, it shrinks. Eventually, it could shrink so much that it collapses under its own immense gravity, forming a black hole. This process would happen without any need for matter as we know it. It is a direct conversion of the energy of a space-time defect into a black hole. The mass of the black hole created would depend on the size of the loop that collapsed. This could potentially create black holes across a huge range of masses. Some could be small, others could be thousands or tens of thousands of solar masses. These larger ones would be perfect seeds for supermassive black holes. They would be born big, giving them a crucial head start. This idea has a certain elegance. It creates massive seeds very early in the universe, solving the timing problem. It also makes a testable prediction. Those oscillating loops of cosmic string should be filling the universe with a background hum of gravitational waves. Our current detectors like LIGO are not sensitive to this kind of background, but a future space-based observatory, the Laser Interferometer Space Antenna LISA, might be. LISA will consist of 3 spacecraft flying in formation millions of miles apart. They will be able to detect much lower frequency gravitational waves than ground-based detectors. If cosmic strings are real and they formed black hole seeds, LISA might hear the leftover chorus of their vibrating loops. Finding that gravitational wave background would be revolutionary. It would be direct evidence of physics from the first moments of the universe's existence. It would also provide a powerful, if strange, explanation for where the first giant black holes came from. The biggest problem with the cosmic string theory is that we have no direct evidence that they exist. They are a compelling theoretical possibility, but so far they remain just that. And they have not been observed. Their effects on the cosmic microwave background have been searched for, but nothing definitive has been found. So, for now, they are a fascinating and wild possibility in the zoo of ideas about black hole origins. Number 17, the first galaxies were built inside dark matter mini-halos. In the standard model of cosmology, the smallest dark matter structures, or halos, to form, were about 1,000,000 times the mass of the Sun. These are called mini-halos. Gas falling into the center of these mini-halos would be the birthplace of the first stars. However, if the gas could cool efficiently and collapse directly without fragmenting into many small stars, it might form a single massive object, a potential seed for a supermassive black hole. This process, known as baryonic collapse, requires very specific conditions, such as the absence of molecular hydrogen, which is a very effective coolant. Ultraviolet radiation from nearby star-forming regions could destroy this molecular hydrogen, creating the perfect conditions for direct collapse. Everything in the universe is built on a scaffold of dark matter. This invisible substance clumped together first, forming vast invisible structures called halos. Normal matter, the gas that would eventually form stars and galaxies, was then pulled by gravity into these halos. The very first halos to form were small. They were called mini-halos, with masses around 1,000,000 times that of our Sun. This is not very big by cosmic standards. Our own Milky Way's dark matter halo is over 1 trillion solar masses. These mini-halos were the cradles of the first cosmic objects. The standard picture is that gas fell into these mini-halos, cooled and fragmented to form the first stars. These were the population the third stars we have already discussed. They would have formed in small clusters at the very center of the mini-halo. But what if the gas did not fragment? What if it all collapsed together into one giant object? This is the core of this theory. It focuses on the specific environment inside those first mini-halos. For gas to collapse and form stars, it needs to cool down. If it stays hot, its own pressure will resist gravity. The main coolant for pristine metal-free gas in the early universe is molecular hydrogen H2. It is not very efficient, but it is all they had. When gas cools via H2, it tends to fragment into many small clumps, each one forming a star. This theory proposes a way to stop this from happening. Imagine a mini halo that is situated near a region where other stars have already formed. Those first massive stars would have been incredibly bright, pumping out huge amounts of ultraviolet UV radiation. This UV light is very effective at destroying molecular hydrogen. It breaks the molecule apart into individual hydrogen atoms. Now, consider the gas falling into our nearby mini halo. It is bathed in this intense UV radiation. Its main coolant, H2, is gone. Without H2, the gas cannot cool down effectively until it gets much hotter and denser. At that point, it can start, cooling through radiation from atomic hydrogen. This is a much, less efficient process and only works at higher temperatures around 10,000 Kelvin. Because the gas stays hotter for longer, its pressure resists fragmentation. Instead of breaking up into hundreds of little stellar mass clumps, the entire massive cloud of gas, perhaps 100,000 solar masses worth, collapses catastrophically toward the center of the mini halo. This is called baryonic collapse. It leads directly to a very massive central object. This object could be a supermassive star that quickly collapses, or it might form a quasi-star, or it might collapse directly into a black hole of around 100,000 solar masses. This is a heavy seed. It is born big. This scenario is attractive because it uses the standard cosmological model of dark matter halos. It just requires some specific environmental conditions. You need a Goldilocks situation. The mini halo must be close enough to a source of UV radiation to have its H2 destroyed, but not so close that the radiation pressure blows all the gas away. The timing has to be just right. This process would have been rare. It would not happen in every mini halo, but it does not need to. You only need to form one supermassive black hole seed per future large galaxy. If this rare process happened occasionally in the early universe, it could explain the origins of the quasars we see. Astronomers are actively looking for evidence of this. The James Webb Space Telescope is capable of seeing the light from these very early assembling galaxies. It might be able to spot the unique signature of a massive gas cloud collapsing in a UV-drenched environment, a galaxy being born with a giant black hole seed already at its heart. Number 16, the missing link is the key. Intermediate mass black holes. IMBHs are a hypothetical class of black holes with masses between 100 and 100,000 times that of the Sun. They are the missing link between stellar mass black holes and supermassive ones. If they exist in large numbers, they could be the building blocks. A young galaxy could form its central black hole by having several IMBHs sink to its center and merge. One of the best places to look for IMBHs is in the centers of globular clusters, which are ancient, dense clusters of stars. The Hubble Space Telescope has found tantalizing evidence for IMBHs in several globular clusters, like Omega Centauri, but the evidence is still debated. A confirmed MBH would be a major breakthrough. We have two well-established families of black holes. There are the stellar mass ones from about 3 to 100 times the Sun's mass. They are the corpses of giant stars. Then there are the supermassive ones, millions to billions of solar masses at the centers of galaxies. There seems to be a huge gap in between. Where are the black holes with masses of, say, 1,000 solar masses? Or 10,000, these are called intermediate mass black holes, or IMBHs. They are the missing link. For a long time, we had no good evidence they even existed. This was a major problem. If supermassive black holes grow from smaller seeds, you would expect to find some of those seeds still lying around. You would expect to see black holes in this intermediate mass range. This theory proposes that IMBHs are not just a consequence of the growth process, but the very key to it. It is a bottom-up approach. It starts with smaller black holes and builds them up. The idea is that the first dense star clusters in the early universe were perfect factories for making IMBHs. Within these clusters, stars are packed so tightly that they often collide. A runaway series of collisions between massive stars could create a very massive star that then collapses into an IMBH. Or the stellar mass black holes formed in the cluster could sink to the center due to a process called dynamical friction. They would interact, merge, and build up into an IMBH. Once you have these IMBHs, you can build a supermassive black hole. Early galaxies were formed from the merger of smaller proto-galaxies. Each of these building blocks might have had its own central IMBH. When these proto-galaxies merged, their IMBHs would eventually find each other. They would spiral in and merge, creating a larger black hole. A few such mergers combined with gas accretion could quickly build a supermassive black hole. This model is appealing because it does not require exotic physics. It uses standard gravitational processes that we know happen. The main challenge has always been the lack of observation. Where are the IMBHs? The hunt for them is one of the most active areas of astrophysics. We are looking for them in a few key places. One is the center of globular clusters. These are old, dense swarms of stars that orbit galaxies like the Milky Way. They are perfect environments for runaway mergers. The Hubble Space Telescope has found hints. By looking at how stars move near the center of a cluster, astronomers can infer the presence of a massive unseen object. Clusters like Omega Centauri and M54 have shown promising signs, but the evidence is not yet conclusive. Another place to look is in dwarf galaxies. These small galaxies might still host their original MBH seeds, which have not had the chance to grow into supermassive black holes. The James Webb Telescope is now looking at these dwarf galaxies with unprecedented detail. Finally, we can look for the gravitational waves from MBH mergers. LIGO and Virgo have detected mergers of stellar mass black holes. The future LISA observatory will be perfectly tuned to detect the mergers of IMBHs and supermassive black holes. If LISA starts detecting the signature of, say, a 10,000 solar mass black hole merging with a 50,000 solar mass black hole, it would be direct proof that this process happens. It would confirm that the missing link exists and that it plays a crucial role in building the giants at the hearts of galaxies. The recent discovery of a few MBH candidates has boosted this theory, but we are still waiting for the smoking gun. Number 15, dark matter itself feeds the first black holes. Normal matter feels pressure and can radiate away heat, which complicates its collapse, and dark matter does not. It only interacts through gravity. In the very dense early universe, some theories suggest that dark matter could have collapsed directly into black holes. Furthermore, a small seed black hole, once formed, could grow primarily by accreting dark matter. In a dense dark matter halo, this could be a very efficient growth mechanism. This process is called gravitational accretion, as opposed to the more complex hydrodynamic accretion of gas. A black hole accreting dark matter would not produce any light, making this phase of its growth completely invisible. This could explain why we do not see the bright signals from the earliest stages of black hole growth. We usually think of black holes growing by eating gas and stars. This is a messy process. The gas heats up as it falls in, creating an accretion disk that shines incredibly brightly. This is what we see as a quasar. The light from this disk creates radiation pressure, which can push away the very fuel the black hole is trying to eat. It is a self-regulating process, and it has a speed limit, the Eddington limit. But what if a black hole could eat something else? Something that does not fight back. This is where dark matter comes in. Dark matter makes up the bulk of the matter in the universe. It is all around the black hole seed at the center of a young galaxy, forming a dense halo. Unlike normal matter, dark matter does not interact with light, it does not heat up, it does not glow, and it does not create any radiation pressure. It only feels gravity. This theory proposes that a significant portion of a supermassive black hole's early growth comes from directly accreting dark matter particles. A small seed black hole, perhaps 100 solar masses, sits at the center of a dense dark matter halo. Particles of dark matter orbit within this halo. Any particle whose orbit takes it too close to the black hole within its capture radius will be swallowed. There is no accretion disk, no light, no outward pressure. It is a clean, efficient, and completely invisible way to grow. The growth rate depends on the density of the dark matter halo and the properties of the dark matter particles themselves. In the densest halos in the early universe, this process could have been very rapid. A seed black hole could have increased its mass by a large factor just by passively consuming the dark matter around it. This would give it a huge head start before it even started to accrete significant amounts of normal baryonic matter. This idea has several attractive features. It helps solve the timing problem by providing a fast and efficient growth channel. It also explains why we do not see many moderately luminous quasars in the very early universe. If the first phase of growth is dark, we would not expect to see them. We would only see the black holes once they become massive enough to start accreting normal gas in a dramatic fashion, turning on as the bright quasars we observe. There are challenges, of course. The efficiency of this process depends on the exact nature of dark matter. If dark matter particles are very fast-moving, hot, or if they have a tendency to annihilate each other, this process would not work well. The model works best with cold dark matter that can form very dense cusps at the centers of halos. We also do not know how to test this theory directly. Since the process is invisible, we cannot observe it happening. We can only infer it. We can build simulations of galaxy formation that include dark matter accretion and see if they better match the observed population of supermassive black holes. If our models consistently fail to grow black holes fast enough using only gas, but succeed when dark matter accretion is included, that would be strong circumstantial evidence. It is a reminder that the story of galaxy formation is not just about the stars and gas we can see. The invisible majority of matter might be playing a leading role, secretly feeding the monsters in the dark. Number 14 dark stars preceded the first normal stars. A dark star is a theoretical object from the early universe, much larger and puffier than a modern star like our Sun. It would have been powered not by nuclear fusion, but by the annihilation of dark matter particles within its core. These stars could have grown to be millions of times the mass of the Sun and shone for millions of years. Once their dark matter fuel was exhausted, they would collapse under their own gravity, potentially forming a massive black hole directly, without a supernova explosion. This would create a heavy seed of up to 1 million solar masses, providing a significant head start for building a supermassive black hole. Before the first stars ignited with nuclear fusion, the universe might have been lit by a different kind of fire. This fire would have been powered by dark matter. The objects it powered are called dark stars. This theory is a fascinating blend of particle physics and astrophysics. It relies on a specific type of dark matter, weakly interacting massive particles, or WIMPs. WIMPs are a leading candidate for dark matter. A key property of many WIMP models is that they are their own antiparticles. When two WMPs meet, they can annihilate each other, releasing a burst of energy. Here is how a dark star would form. In the early universe, a large cloud of pristine hydrogen and helium gas would begin to collapse under its own gravity at the center of a dark matter mini-halo. This is the same starting point as for the first normal stars, but the center of this mini-halo would have a very high density of dark matter WIMPs. As the gas cloud collapses and becomes denser, it pulls even more dark matter into its core. The density of both gas and dark matter becomes immense. At a certain point, the WIMPs in the core become so crowded that they start annihilating each other frequently. This annihilation releases a lot of energy. This energy heats the surrounding gas. This heat creates outward pressure, which fights against gravity and stops the gas cloud from collapsing further into a compact, fusion-powered star. Instead, it creates a new, stable equilibrium. The object becomes a dark star. It is not dark in the sense of being invisible. It would have been very bright, but its energy source is dark in the sense that it comes from dark matter, not fusion. These dark stars would have been bizarre objects. They would not be the hot, dense balls we think of as stars. They would have been enormous, puffy, and relatively cool. A dark star could grow to be millions of times the mass of our sun, but its surface temperature would only be around 10,000 Kelvin. It would be a giant luminous cloud. A dark star could continue to grow as long as it could pull in more gas, and as long as there was enough dark matter in its core to annihilate and provide energy. It could live for millions of years, but eventually the dark matter fuel in the core would run out. The annihilation rate would drop. When that happens, the energy source that was holding the star up vanishes. With its support gone, the dark star would collapse catastrophically under its own immense gravity. A star of millions of solar masses would not explode. It would collapse directly into a black hole of a similar mass. This process would create a very heavy black hole seed, 1,000,000 solar masses or more, right at the beginning of a galaxy's life. This is a very effective solution to the timing problem. You start with a seed that is already a supermassive black hole in its own right. The biggest challenge for this theory is that it depends on dark matter being WIMPs with the right properties for annihilation. The decades of experiments on Earth have been searching for WIMPs, but so far none have been found. The constraints are getting tighter and tighter, and many of the simplest WIMP models have been ruled out. However, if WIMPs do exist, then dark stars are a plausible, almost necessary consequence of cosmology. The James Webb Telescope might be able to find them. Because they are so large and relatively cool, they would have a unique spectral signature. Finding an object with the mass of 1,000,000 suns but the temperature of a much smaller star in the early universe would be a smoking gun for a dark star, and a revolutionary clue to the nature of dark matter and the origin of black holes. Number 13, supermassive stars were the first step. Before galaxies were filled with billions of smaller stars, the universe might have created single, colossal stars with masses up to 1,000,000 times that of our sun. These are called supermassive stars. They would have formed from the direct, rapid collapse of enormous clouds of pristine gas. Because they lacked heavy elements, they would be very different from modern stars. They would be held up by radiation pressure and burn through their fuel in only a couple of million years. A supermassive star would be too massive to explode in a supernova. When its life ended, it would become unstable and collapse directly into a black hole of a similar mass, forming a heavy seed of 100,000 solar masses or more. The very first stars, the population the third stars, were thought to be big, perhaps a few hundred times the mass of the sun. But what if the universe was capable of making something much, much bigger? You know, this theory proposes the existence of supermassive stars. These are not just slightly larger versions of normal stars. They are a completely different class of object with masses ranging from 10,000 to over 1,000,000 times the mass of our sun. The conditions for forming such a beast would have to be perfect. You would need a massive cloud of pristine, metal-free gas in the early universe, perhaps 1,000,000 solar masses in total. This cloud would need to collapse very rapidly, funneling material to its center at an enormous rate, perhaps as high as 1 solar mass per year. This rapid inflow of material is crucial. It overwhelms the normal processes that would cause the cloud to fragment into smaller stars. Instead, a single, gigantic object forms at the center. This object would not be powered by nuclear fusion in the same way as the sun. For a star, this massive would be so hot and dense in its core that the radiation it produces creates an immense outward pressure. This radiation pressure, not the gas pressure from fusion, is what would hold the star up against its own crushing gravity. It would be a delicate balancing act. These supermassive stars would have had very short and violent lives. They would burn at incredibly high temperatures. Their lifespan would be just a couple of million years, a mere blink of an eye in cosmic terms. Our sun, by contrast, will live for about 10 billion years. The end of a supermassive star's life would be just as dramatic as its formation. As a star this massive is inherently unstable, it is too big to go supernova, an explosion could not overcome the intense gravity. Instead, when its fuel runs out and the outward radiation pressure falters, the star would undergo a process called relativistic instability. It would collapse completely. The entire mass of the star, hundreds of thousands or even a million solar masses, would fall inward to form a black hole. This process creates a heavy seed in one go. You skip all the intermediate steps of forming smaller black holes and merging them. You start with a seed that is already massive, around 10,000 to 100,000 solar masses or more. This gives you a massive head start in the race to build a billion solar mass quasar. This scenario is a leading contender in the heavy seed category of models. The physics is plausible, although the conditions required are extreme. The main question is whether those conditions, particularly the extremely high gas inflow rates, were common in the early universe. Cosmological simulations are used to try to answer this. They model the evolution of gas and dark matter and look for places where these supermassive stars could have formed. The results are promising but not yet conclusive. It seems possible that such objects could form in the centers of the most massive, earliest dark matter halos, like other heavy seed models. This one predicts that supermassive black holes should have a minimum mass. You would not expect to find many black holes with masses between the stellar mass range around 100 solar masses and the mass of these seeds around 10,000 solar masses. This mass gap is something astronomers are actively searching for. Finding it would be strong support for the idea that black holes started big. Number 12, it was a violent demolition derby. In the heart of a dense young star cluster, stars are packed together a million times more tightly than in our solar neighborhood. In such an extreme environment, direct physical collisions between stars would be common. This theory suggests a runaway process where one star, through a series of mergers, grows progressively larger. A massive star collides with another, and the merged product is even more massive, making it an even bigger target for future collisions. This chain reaction could create a very massive star, perhaps 1,000 times the mass of the sun, in a very short time. This star would then collapse to form an intermediate mass black hole, a seed for a larger supermassive black hole. Imagine a place where stars are not distant points of light, but are packed together like cars in a traffic jam. This is the environment at the center of a dense globular cluster, or a young galactic nucleus. In these places, the density of stars can be 1,000,000 times higher than in the neighborhood of our sun. Here, gravity is king, and things get violent. This theory proposes that the first black hole seeds were forged in a cosmic demolition derby. It is called the runaway stellar collision model. It works like this. You start with a very dense cluster of stars. The most massive stars in the cluster tend to sink toward the center. This is a process called mass segregation, driven by an effect known as dynamical friction. It is like a bowling ball moving through a crowd of ping pong balls. The bowling ball quickly loses energy and settles in the middle. So you end up with a core of massive stars in this crowded central region. Direct collisions are not just possible, they are inevitable. When two stars collide and merge, the result is a new, more massive star. This new star has an even larger gravitational influence and a larger physical size, making it an even more likely target for the next collision. This can trigger a runaway process. One star starts to grow uncontrollably by swallowing its neighbors. One merger leads to another and another. In a very short period of time, perhaps only 1,000,000 years, this runaway process could build a single, extremely massive star with a mass of several hundred or even a few thousand solar masses. This superstar would not live long. It would burn through its fuel at a furious rate. When it dies, it would be too massive to explode in a typical supernova. It would collapse directly into a black hole. The result would be an intermediate mass black hole, or IMBA, of a few hundred to a few thousand solar masses. This provides a natural way to form the missing link black holes. Once you have this MBH seed at the center of the star cluster, it can continue to grow. It can swallow any stars that stray too close. It can merge with other stellar mass black holes in the cluster. And if this star cluster is the nucleus of a young galaxy, the IMBA is perfectly positioned to become the seed for the central supermassive black hole. This model is attractive because it relies on well-understood physics. We know how gravity works in dense clusters. We can simulate these collisions on computers. The simulations show that this runaway process is plausible under the right conditions, specifically in very dense and compact star clusters. The challenge is whether these conditions were common enough in the early universe. Were the first star clusters dense enough to drive this process? And could the resulting IMBHs grow fast enough to explain the early quasars? This model creates seeds that are heavier than a single star's collapse light seeds, but not as massive as the direct collapse model's heavy seeds. They are in the middle, so they still face a challenge in growing to 1 billion solar masses in time. However, this process could be a very common way to create IMBHs, which, as we have seen, could then merge to form larger black holes. So it may not be the single solution, but it could be a crucial part of the overall puzzle, a key mechanism for building the first big seeds from scratch. Number 11, galaxies merged, and so did their black holes. Galaxies are not static islands. They grow by colliding and merging with other galaxies over cosmic time. Our own Milky Way is on a collision course with the Andromeda Galaxy, set to merge in about 4.5 billion years. When two galaxies merge, their central supermassive black holes will also eventually merge. Over billions of years, a black hole can grow through a series of these mergers. This process, known as hierarchical merging, is a fundamental part of our understanding of galaxy evolution. Gravitational wave observatories like LIGO and Virgo have directly observed the mergers of stellar mass black holes, proving that this process happens. The future LISA observatory is designed to detect the much more powerful gravitational waves from the mergers of supermassive black holes. This is less of a theory about how the first seeds formed, and more about how those seeds, once they exist, grow to become giants. It is a fundamental piece of the puzzle. The idea is simple galaxies grow by merging, and when they do, their central black holes merge too. We live in a universe governed by a hierarchical model of structure formation. This means small things formed first, and then they merged over time to create bigger things. Small dark matter halos merge to form bigger halos. Small galaxies merge to form bigger galaxies like our Milky Way. It is a process of cosmic consolidation that continues to this day. Our own galaxy shows the scars of this history. We can see streams of stars that are the shredded remnants of smaller dwarf galaxies that the Milky Way has consumed. The process is dramatic. When two galaxies of similar size collide, gravity reshapes them over hundreds of millions of years. Their stars and gas clouds are thrown into disarray. At the heart of each of these merging galaxies is a supermassive black hole. As the galaxies merge, these two black holes are drawn towards the center of the new, larger galaxy. They begin to orbit each other, forming a supermassive black hole binary. This binary pair continues to lose energy. At first, it does so by flinging nearby stars out of the galactic center, a process called the gravitational slingshot. The black holes get closer and closer. Eventually, when they are very close, they start to radiate a huge amount of energy away in the form of gravitational waves. These are the ripples in spacetime that LIGO and Virgo can detect. This radiation of gravitational energy causes the black holes to spiral in faster and faster until they finally collide and merge into a single, more massive black hole. This new black hole will be spinning rapidly and will receive a kick from the merger, which can send it recoiling from the galactic center, though usually not by enough to escape. This process is a key way to grow black holes. If a galaxy undergoes several major mergers over its lifetime, its central black hole can grow substantially. A merger between 200 million solar mass black holes results in a nearly 200 million solar mass black hole. This hierarchical merging is a crucial ingredient in all models of supermassive black hole growth. The evidence for galaxy mergers is everywhere we look. We see pictures of interacting galaxies with tidal tails and distorted shapes all over the sky. We have also seen the results of this process, the direct detection of gravitational waves from merging stellar mass black holes by LIGO and Virgo. This was a monumental discovery that confirmed Einstein's theory and proved that black hole mergers happen. However, LIGO cannot detect the low-frequency waves from supermassive black hole mergers. That will be the job of the future. Laser Interferometer Space Antenna LISA. LISA will be an observatory in space capable of hearing the gravitational symphony of the universe, including the cataclysmic mergers of monster black holes at the centers of distant galaxies. When LISA flies, it will provide the ultimate test of this idea. It will tell us how often supermassive black holes merge, how massive they are, and how they spin. It will transform our understanding, but hierarchical merging on its own is not the whole story. It explains the growth, but not the origin of the seeds, and it might be too slow to explain the most distant, massive quasars. A merger takes time. It takes time for the galaxies to merge, and more time for the black holes to sink to the center and finally coalesce. Doing this enough times to build a billion solar mass black hole in just a few 100 million years is a tall order. So while merging is undoubtedly important, it must be combined with another process like rapid gas accretion to explain the early giants. Number 10. The universe's first objects were quasi-stars. A quasi-star is a hypothetical object that may have existed in the early universe. It would look like a giant star from the outside, but its core would not be powered by fusion. Instead, at its center would be a growing black hole. Gas falling toward the central black hole would release enormous amounts of energy. This energy would inflate the surrounding gas into a huge luminous envelope, thousands of times the size of our solar system. A quasi-star could have lived for a few million years, during which the central black hole could grow to several thousand solar masses. When the envelope was finally blown away, it would leave behind an intermediate mass black hole, a perfect seed. In the quest to understand how black holes get big fast, some theories have imagined objects that are not quite stars and not quite black holes, but something in between. One of the most intriguing of these is the quasi-star. A quasi-star is essentially a black hole wearing a star as a giant, puffy coat. The story begins with the collapse of a massive gas cloud in an early dark matter halo. This is the same starting point as for a supermassive star. However, in this scenario, as the central core of the cloud becomes incredibly dense, it collapses to form a small black hole, perhaps only 10 or 20 solar masses, while the rest of the massive gas cloud is still falling inward. You now have a small black hole embedded within its own enormous gaseous cocoon. The gas continues to fall towards this central black hole. As it does, it releases a tremendous amount of gravitational potential energy. This energy heats the surrounding gas, creating an immense outward pressure. This pressure halts the collapse of the rest of the cloud. The system reaches a strange kind of equilibrium. It is a giant, bloated object that looks like a star from the outside. It could be 1 billion miles across and as luminous as a small galaxy, but its power source is not nuclear fusion in its core. Its power source is accretion onto the central black hole. This is why it is called a quasi-star. From the outside, you would see a very luminous but relatively cool photosphere. It would look like a red supergiant star, but on a scale never seen before. It would have a surface temperature of only a few thousand degrees Kelvin, much cooler than the sun. The key thing about a quasi-star is that it provides a way to grow a black hole very, very quickly without being stopped by radiation pressure. In a normal accretion disk, the radiation can blow away the fuel, but in a quasi-star, the infalling gas is so dense and optically thick that the energy is trapped. The radiation helps to hold the envelope up, but it cannot escape to stop the inflow. The central black hole can accrete material at a huge rate, far above the normal Eddington limit. The quasi-star phase might last for a couple of million years. During this time, the central black hole steadily grows. It starts at maybe 20 solar masses and can grow to several thousand solar masses. Eventually, the black hole becomes so massive that the energy it releases is enough to finally blow away the surrounding gas envelope. When the dust settles, what is left behind is an intermediate mass black hole of a few thousand solar masses, sitting right at the center of its host halo. This gives you a fairly massive seed, created very quickly. The quasi-star model is a specific type of heavy seed model. It is an elegant way to bypass the Eddington limit and grow a seed quickly. The main uncertainty is whether the conditions to form one ever really existed. Do massive collapsing clouds really form a central black hole before the whole thing turns into a star? Our computer simulations are still trying to figure out the complex physics involved. Like dark stars, quasi-stars would have a unique observational signature. The James Webb Telescope could potentially spot one. Finding a very large, very bright, but very cool object in the early universe would be strong evidence for this strange transitional phase of matter, a star powered by a black hole heart. Number 9, black holes broke their own speed limit. The Eddington limit is a theoretical speed limit on how fast a black hole can grow. It is the point at which the outward pressure of the light from the hot infalling gas exactly balances the inward pull of gravity. If you try to shovel gas in faster than this, the light should blow the gas away. However, some theories suggest that under certain conditions, black holes can accrete material much faster than this limit. This is called super Eddington accretion. For example, if the gas comes in through a very thick, clumpy disk, some of it might be shielded from the radiation and fall in anyway. Sustained periods of super Eddington accretion could allow a small, stellar, mass seed black hole to grow to 1 billion solar masses in the time available in the early universe. There is a speed limit for eating in the universe. It is called the Eddington limit. It is a fundamental concept in astrophysics. When gas falls onto a compact object like a black hole, it gets very hot and shines brightly. This light, this radiation exerts a pressure, it pushes outward. Gravity, meanwhile, is pulling the gas inward. The Eddington limit is the point of perfect balance. It is the maximum rate at which a black hole can accrete gas, where the inward pull of gravity is exactly balanced by the outward push of radiation pressure. If you try to feed the black hole any faster, the theory says the intense light should just blow the extra fuel away. This is a huge problem. If you take a typical stellar mass black hole, say 100 solar masses, and let it grow at the Eddington limit, it takes a very long time to get big. The mass grows exponentially, but the E-folding time, the time to increase its mass by a factor of E, about 2.718 is about 45 million years. To get from 100 solar masses to 1 billion solar masses would take many hundreds of millions of years. This is longer than the age of the universe when we see the first giant quasars. So if black holes started small, they must have broken the speed limit, they must have undergone super Eddington accretion. This theory explores how that could be possible. The standard Eddington limit calculation assumes everything is nice and spherical. The gas falls in from all directions, and the radiation goes out in all directions. But what if the situation is not so simple? The real universe is clumpy and messy. One idea is that the accretion disk around the black hole is not the thin, flat pancake we often imagine. It could be a thick, puffy, turbulent donut. This is called an advection-dominated accretion flow, or a slim disk. In this kind of disk, the gas is so dense that it traps the radiation. The heat does not escape efficiently. Instead, it gets swept along with the gas and falls into the black hole. The black hole effectively swallows its own exhaust fumes. This means the outward radiation pressure is much lower than you would expect, allowing the accretion rate to be much higher. Another possibility is that the gas does not come in smoothly. It might come in as dense clumps. The outer layers of a clump might be blown away by radiation, but the dense inner core could be shielded and punched through to the black hole. It is like trying to put out a bonfire with a garden hose versus throwing a bucket of water on it. The bucket gets through. These scenarios allow for short bursts of accretion at rates 10, 100, or even 1,000 times the Eddington limit. If a young black hole could sustain this kind of rapid growth for several million years, it could bulk up very quickly. This would allow a light seed from a population the third star to grow into a monster in the short time available. The evidence for super Eddington accretion is growing. We see some objects in the nearby universe called ultraluminous X-ray sources, ULXs, that appear to be stellar mass black holes accreting well above their Eddington limits. This suggests the process is physically possible. The challenge is making it happen consistently for millions of years in the early universe. The conditions have to be just right. You need a huge, continuous supply of gas being funneled into the very center of a young galaxy. But if this can happen, it provides a way for even the smallest seeds to grow into giants by simply ignoring the cosmic speed limit. Number 8, they came from the very beginning. Primordial black holes, PBHs, are a hypothetical type of black hole that would have formed in the first second after the Big Bang. They would not have formed from the collapse of a star. Instead, they would have formed from the direct collapse of extremely dense regions of matter and energy in the turbulent early universe. This process could have created black holes with a very wide range of masses, from less than a gram to many thousands of times the mass of the Sun. If PBHs with masses of 10,000 solar masses or more were created, they would be perfect, ready-made seeds for supermassive black holes. They would exist before the first stars and galaxies. Most theories of black hole formation start with stars or gas clouds. But what if the very first black holes needed neither? What if they were born in the fire of the Big Bang itself? This is the idea behind primordial black holes, or PBHs. They are a concept that dates back to the 1970s, proposed by Stephen Hawking and Bernard Carr. In the first moments after the Big Bang, the universe was an incredibly dense and violent place. It was not perfectly smooth. There were tiny fluctuations in density from place to place. In most regions, these fluctuations were small. But in some places, by pure chance, the density might have been much higher than average. If a region was dense enough, its own gravity could overwhelm the outward pressure of the hot plasma. The entire region would collapse directly into a black hole. This process is completely different from stellar collapse. It does not require a star to live and die. It is a direct consequence of the initial conditions of the universe. This could have happened in the first fraction of a second of the universe's existence. The mass of a PBH would depend on the size of the density fluctuation that created it. This means PBHs could, in principle, form with almost any mass. Some could have been microscopic, with the mass of an asteroid but the size of an atom. These tiny ones would have evaporated by now due to Hawking radiation. Others could have been more massive, a few times the mass of the Sun. And some could have been truly enormous, with masses of thousands or tens of thousands of solar masses. These larger PBHs are the ones that are interesting for our story. If they were formed, they would have been created before the first stars and galaxies. They would be ready-made seeds. A young galaxy would not need to create a seed. It would just need to capture a pre-existing PBH, or form around one that was already there. This would completely solve the timing problem. You do not need to wait for stars to form and die. The seeds are present from time zero. The PBH theory is compelling, but it has a big problem. We have no proof that they exist. Their existence is very sensitive to the conditions in the very early universe, which we do not fully understand. Scientists have looked for evidence of them for decades. We can place constraints on how many of them there can be. If there were too many PDHs of a certain mass, they would have affected the cosmic microwave background, the formation of the first elements, or the distribution of galaxies in ways that we do not see. There have been searches for them using gravitational lensing, where a PDH passing in front of a distant star would briefly make it appear brighter. So far, these searches have come up empty for most mass ranges. There is another fascinating aspect to PDHs. For a long time, they've been considered a candidate for dark matter. Perhaps the dark matter that holds galaxies together is not a new type of particle, but a huge population of planet mass PDHs. However, recent observations have put very tight constraints on this idea. But even if they do not make up all of dark matter, a small number of more massive PDHs could still exist. They could be the seeds we are looking for. The detection of gravitational waves by LIGO and Virgo has opened a new window. Some of the black hole mergers that have been detected involved black holes that were heavier than expected from standard stellar evolution. This has led some to speculate that these could be primordial black holes. If we ever detect the merger of a black hole in the mass gap between stellar and supermassive black holes, it could be a sign of a PDH. It remains a tantalizing, if unproven, possibility. Number 7, gas clouds collapsed without making stars. Under normal conditions, a large cloud of gas in a galaxy will cool and fragment into many smaller clumps, which then form a cluster of stars. This theory proposes a special set of circumstances in the early universe where a massive gas cloud, weighing perhaps 100,000 solar masses, could collapse directly to form a black hole without fragmenting into stars at all. This is called a direct collapse black hole DCBH. This requires the gas to stay warm and resist breaking up. One way to achieve this is to have a nearby source of ultraviolet radiation that destroys molecular hydrogen, the main coolant for the gas. Without this coolant, the whole cloud collapses catastrophically into a single object, forming a heavy seed of 10,000 to 100,000 solar masses. This is one of the leading theories for how supermassive black holes got their start. It is an elegant way to make a very big seed very quickly. It is called the direct collapse black hole, or DCBH, model. The basic idea is to skip the star part of star formation. Normally, when a giant cloud of gas starts to collapse under its own gravity, it does not all fall to the center at once. It fragments. Pockets of the cloud become dense and collapse on their own, forming hundreds or thousands of individual stars. You end up with a star cluster. The DCBA model proposes a way to stop this fragmentation. The goal is to get the entire gas cloud, 100,000 solar masses or more, to collapse as a single unit. To do this, you need to control how the gas cools. Gas pressure is what resists gravity. Hot gas has high pressure. As a cloud collapses, it gets compressed and heats up. To keep collapsing, it needs to radiate that heat away. In the pristine gas of the early universe, the most important coolant molecule was molecular hydrogen, H2. It is not a great coolant, but it is all they had. H2 allows the gas to cool to a few hundred degrees Kelvin. At this temperature, the cloud becomes unstable and shatters into many small pieces, which then form stars. The key to direct collapse is to get rid of the molecular hydrogen. How do you do that? You need to expose the gas cloud to a strong bath of ultraviolet UV radiation. Specifically, you need UV photons with just the right energy to break the H2 molecule apart. This is called Lyman-Werner radiation. Imagine a pristine gas cloud in a dark matter halo. This halo has to be what we call an atomic cooling halo, meaning it is massive enough that the gas can cool via radiation from atomic hydrogen. But this only works when the gas is very hot, around 10,000 Kelvin. Now, imagine this halo is located near a young star-forming galaxy. This neighbor galaxy is blazing with the light of the first massive stars, which are pumping out huge amounts of Lyman-Werner photons. Our gas cloud is bathed in this radiation. Any H2 that tries to form is immediately destroyed. Without its main coolant, the gas cloud cannot cool down efficiently. It stays hot around 10,000 K. The high temperature gives it a strong internal pressure, which prevents it from fragmenting. The entire cloud, all 100,000 solar masses of it, continues to collapse as one coherent object. It funnels down to the center of the halo, forming either a supermassive star or a quasi-star, which then quickly collapses into a black hole of 10,000 to 100,000 solar masses. You have created a heavy seed in one step. This model is very appealing. It solves the time problem by starting with a massive seed. It also relies on conditions that, while specific, were likely to exist in some places in the early universe. You just need the right combination of a massive halo and a nearby source of UV light. The James Webb Space Telescope is perfectly suited to search for these objects. It is looking for very red objects in the early universe. A collapsing DCBH or the supermassive star it forms would be very luminous, but also shrouded in gas and dust, making it appear very red. Finding one would be a major discovery. It would provide strong evidence that black holes can be born big, bypassing the slow, gradual process of stellar evolution. Number 6, it all started with the first stars. The very first stars in the universe, known as population, the third stars, were very different from our sun. They formed from pure hydrogen and helium, the elements created in the Big Bang. Because they lacked heavier elements or metals, they could grow to enormous sizes, perhaps 100 to 300 times the mass of the sun. These massive stars lived very short, very brilliant lives, lasting only a few million years. When they died, they were too massive to explode in a typical supernova. Instead, their cores collapsed directly into black holes, leaving behind light seeds with masses of about 100 to 250 solar masses. These seeds would then have to grow incredibly rapidly to become the supermassive black holes we see. This is the classic, most straightforward idea. It is the light seed model. It starts with the very first stars to ever exist. These were called population the third stars. We have never seen one directly. They are a theoretical prediction, but a very solid one. They formed a few 100 million years after the Big Bang out of the pristine gas of hydrogen and helium left over from the initial fireball. The modern stars, like our sun, a population I star, are contaminated with heavier elements like carbon, oxygen, and iron. These elements were forged inside previous generations of stars and scattered through space when those stars died. These metals, as astronomers call them, are very important. They change how a gas cloud cools and collapses. Metal-rich gas cools very efficiently, which tends to make it fragment into many small stars. The gas in the early universe had no metals. This made it much harder for the gas to cool. Because it stayed warmer, it tended to form much more massive stars. So while a typical star in the Milky Way today might be about half the mass of the sun, a typical population the third star was probably 100 times the mass of the sun, or even more. Some could have reached 300 solar masses. These stars would have been giants, incredibly hot and bright. They would have blazed with a fierce blue-white light, but they lived fast and died young. A star's lifespan is determined by its mass. The more massive it is, the faster it burns through its fuel. A 100 solar mass star would live for only a couple of million years. Our sun, in contrast, will live for 10 billion. The death of these first stars would have been spectacular. A star between about 140 and 260 solar masses would die in a pair instability supernova, an incredibly violent explosion that would have blown the star completely apart, leaving nothing behind, no black hole. But stars more massive than about 260 solar masses would have met a different fate. Their cores would have become so hot that they would collapse under their own immense gravity. The collapse would be total and catastrophic. The entire star would fall into a black hole without a major explosion. This would leave behind a black hole with a mass of about 100 to 250 solar masses. These are the light seeds. This is a very natural and appealing starting point. The first stars had to exist, and their massive members had to collapse into black holes. So these seeds must have been created. The problem is not their formation, but their growth. This is the biggest challenge for the light seed model. You start with a seed of, say, 150 solar masses. You need to grow it to 1 billion solar masses by the time the universe is 700 million years old. That is an enormous increase in mass in a very short amount of cosmic time. As we have discussed, growing at the normal Eddington limit is far too slow. To make this model work, you need to invoke something extra. You need sustained periods of super Eddington accretion, where the black hole is fed at a furious rate. Or you need a lot of mergers with other black holes and dense star clusters. So while the formation of light seeds is almost guaranteed, they create a severe timing problem. It is like giving a baby a deadline to become a heavyweight champion in a few months. It is not impossible, but it requires an extreme and sustained training and feeding regimen. Many astronomers believe this is the most likely path, and the challenge lies in understanding the complex physics of gas accretion that would allow these seeds to grow so quickly. Number 5, the process was inefficient and messy. Black hole growth is not a smooth, continuous process. It is regulated by feedback. As a black hole accretes gas, the accretion disk heats up and shines brightly, becoming a quasar. This intense radiation, along with powerful jets and winds launched from the disk, can heat the gas in the host galaxy and blow it away. This starves the black hole of its fuel, shutting off its growth. The galaxy then cools down, gas falls back to the center, and the process starts again. This cycle of on and off phases means a black hole might spend much of its time not growing at all. This feedback is essential for explaining why supermassive black holes have the masses they do and why they are not even larger. We often talk about black holes growing as if they are just sitting at a buffet, eating as much as they want. The reality is much more complicated and much messier. The process of growing a black hole is inherently self-destructive. This is the concept of feedback. When a supermassive black hole is actively accreting gas, it becomes an active galactic nucleus AGN, or a quasar. The accretion disk around it can outshine all the billions of stars in its host galaxy combined. This incredible output of energy has a profound effect on the galaxy. It does not just sit there. It pushes back. There are several forms of feedback. First, there is radiation pressure. The intense light from the quasar can exert a physical push on the gas and dust throughout the galaxy. Second, there are powerful winds. These are outflows of hot gas driven away from the accretion disk at high speeds. Third, in some cases there are relativistic jets. These are focused beams of particles and energy launched from the poles of the black hole at nearly the speed of light. They can travel for hundreds of thousands of light years, punching giant cavities into the gas surrounding the galaxy. All of these feedback mechanisms heat up the gas in the galaxy and can drive it out of the galactic core, or even out of the galaxy altogether. This is a form of self-regulation. The black hole needs a supply of cold gas to grow, but the very act of growing heats and expels that gas. So the black hole effectively chokes itself off. It starves itself. Once the fuel supply is cut off, the quasar turns off, the black hole stops growing. The galaxy then has time to recover. The gas can cool down, and eventually it will start to fall back towards the galactic center. This can reignite the quasar, and the cycle begins again. This feedback loop is crucial for our understanding of galaxy evolution. It explains one of the biggest mysteries why our galaxies and their black holes the size they are. Without feedback, simulations predict that galaxies should be much larger and more star-filled than we observe. and their central black holes should be monstrously bigger. Feedback is the regulatory valve that keeps things in check. It creates a tight connection between the growth of the black hole and the growth of the galaxy itself. This is believed to be the origin of the M-sigma relation, the observed correlation between a black hole's mass and the properties of its host galaxy's bulge. The black hole's growth influences the galaxy's star formation, and the galaxy's gas supply influences the black hole's growth. They evolve together, but this also makes the timing problem for early quasars even harder. If black holes spend a lot of their time dormant because they have blown their fuel away, it means the time they have available for actual growth is even shorter. The growth must be even more rapid and efficient during the brief on phases. So any successful theory of supermassive black hole formation must not only explain how the seeds are made, but also how they can grow in this chaotic, self-regulating environment of violent feedback. It adds a layer of complexity and realism to the entire problem. Number 4, the problem is not making them, it is seeing them. It is possible that the early universe was full of growing supermassive black holes, but that most of them were hidden from our view. The first galaxies were very rich in gas and dust. A growing black hole seed at the center of such a galaxy would have been deeply enshrouded in this material. This gas and dust would absorb most of the light from the accretion disk, making it invisible to our telescopes. We might only be seeing the rare, unobscured tip of the iceberg. The James Webb Space Telescope, with its powerful infrared capabilities, is designed to peer through this cosmic dust and find this hidden population of growing black holes. Perhaps we are looking at the problem all wrong. We are troubled by the fact that we see a few billion solar mass black holes so early in the universe. We wonder how they could have grown so fast, but what if the problem is not that their growth was exceptional, but that our view is biased? This is the obscuration argument. The early universe was a very different place. The galaxies were smaller, but they were also much denser and richer in gas and dust. The very fuel that a black hole needs to grow is also the perfect screen to hide it. Imagine a light seed black hole, 100 solar masses at the center of a young gas-rich galaxy. It starts accreting gas rapidly, it becomes very luminous, but it is surrounded by a thick, dense cocoon of gas and dust. This material is opaque. The powerful X-rays and ultraviolet light from the accretion disk are absorbed by this cocoon. The cocoon heats up and re-radiates the energy at longer infrared wavelengths. From our perspective on Earth, we would not see a brilliant quasar. We would see a dusty infrared bright blob. We would have no direct sign of the powerful engine hidden within. We would be completely unaware of the rapid growth happening inside. According to this idea, the early universe could have been teeming with these obscured, growing black holes. The ones we see as bright, unobscured quasars are just the rare exceptions. Perhaps their host galaxy has undergone a recent merger that cleared out the gas and dust from our line of sight. Or perhaps we just happen to be looking down a cleared-out polar axis, while the dusty donut of material blocks the view from other angles. We are only seeing the tip of the iceberg. The vast majority of the black hole population at that time is hidden. This would change the picture significantly. It would mean that the process of growing a black hole did not have to be freakishly fast in a few rare cases. It could have been a more common, widespread phenomenon. Many light seeds could have started growing early and rapidly, but most did so in secret. This is a very testable idea. If there is a large hidden population of growing black holes, we should be able to find them. Traditional optical telescopes cannot, but the James Webb Space Telescope can. JWS is an infrared telescope. It is specifically designed to see the universe at the longer wavelengths that can penetrate through dust. It is now hunting for these hidden monsters. It is looking for galaxies in the early universe that are unusually red and bright in the infrared. This could be the telltale signature of a powerful dust-shrouded quasar. If JWST uncovers a large population of these obscured objects, it would mean our census of early supermassive black holes has been massively incomplete. It would ease the timing problem, not by changing the physics of growth, but by revealing that growth was happening everywhere, all along, hidden in plain sight. Number 3, it is not one theory, but all of them. The universe is a big place, and it is unlikely that there was only one single way to form a supermassive black hole. It is highly probable that different mechanisms operated in different environments. In some dense star clusters, runaway collisions might have formed intermediate mass seeds. In some pristine UV-irradiated halos, direct collapse might have occurred. In other places, the collapse of the first stars provided the seeds. This cocktail approach suggests that the population of supermassive black holes we see today is the result of multiple formation channels. This would explain the diversity we see in black hole masses and host galaxy properties. We have been discussing all these different theories as if they are competing in a championship. We are looking for the one winner that explains everything. But what if that is the wrong way to think about it? The universe is vast and complex. It is rarely a case of one size fits all. This theory proposes that there is no single answer. Instead, multiple pathways were at play. It is a cocktail model where different ingredients were mixed in different proportions depending on the local conditions. In one corner of the early universe, you might have had a very dense, compact star cluster. Here, the conditions were perfect for runaway stellar collisions. The result was an intermediate mass black hole of a few thousand solar masses. This was one channel. In another region, you had a pristine, massive gas cloud that happened to be next to a bright, star-forming neighbor. It was bathed in UV radiation, its molecular hydrogen was destroyed, and it underwent direct collapse. This created a heavy seed of 100,000 solar masses. That was a second channel, and everywhere else the very first population of the third stars were forming. Most of them died and collapsed into light seeds of 100 solar masses. This was the third, and perhaps most common, channel. So you have a universe seeded with black holes of all different starting masses. The light seeds from Pop the Third stars are common, but face a difficult, uphill battle to grow. The heavy seeds from direct collapse are rare, but they are born with a huge advantage. The intermediate seeds from cluster collisions are somewhere in between. All of these seeds would then grow through the same processes, gas accretion, and hierarchical mergers. A galaxy that started with a heavy DCBH seed might become home to one of the giant quasars we see at high redshift. A galaxy that started with a light Pop the Third seed might take much longer to grow its central black hole, or it might never grow very large at all. This approach seems very plausible. It would explain the diversity we see in galaxies and their central black holes. It accounts for the fact that the conditions in the early universe were not uniform. Different environments would naturally lead to different outcomes. The challenge for astronomers is to untangle this history. Can we look at a supermassive black hole today and tell how it started its life? Well, there might be clues. For example, the spin of a black hole might hold a memory of its formation. A black hole formed from the direct collapse of a single rotating cloud might be born spinning very fast. A black hole built up from many random mergers of smaller black holes might end up with a much lower spin. Future observations, especially with gravitational wave detectors like LISA, which can measure black hole spins, might allow us to perform this kind of cosmic archaeology. We might be able to distinguish between different formation channels by looking at the properties of the black holes themselves. The answer to the question, how do supermassive black holes form, might not be a single sentence, but a complex story with multiple plot lines. Number 2, the question itself is based on a flawed assumption. Our models of cosmology are based on cold dark matter CDM, which is assumed to be slow-moving and collisionless. But what if dark matter has properties we do not expect? For example, if dark matter can interact with itself, it could change how the first dark matter halos form. Self-interacting dark matter could lead to the formation of denser central cores and halos. which would accelerate the collapse of gas and the formation of black hole seeds. Alternatively, if dark matter is warm instead of cold, it would suppress the formation of small-scale structures, leading to the formation of more massive galaxies and black holes from the start. Our confusion about black hole formation might be a sign that our underlying cosmological model is incomplete. We have spent all this time trying to solve a puzzle. The puzzle is how to grow a black hole to 1 billion solar masses so quickly. All of our attempts to solve it are based on our current understanding of the universe. This understanding is encapsulated in the lambda-cold dark matter LCDM model of cosmology. It has been incredibly successful at explaining a vast range of observations, from the cosmic microwave background to the large-scale distribution of galaxies. But what if the puzzle is hard because one of our starting assumptions is wrong? What if our confusion about supermassive black hole formation is not a problem with our theories of stars and gas, but a crack in our fundamental model of cosmology? Let's look at the CDM part, cold dark matter. Cold means the dark matter particles were moving slowly in the early universe. This allows them to clump together easily and form structures on all scales, from small mini halos to giant clusters. This is what leads to the hierarchical bottom-up formation of galaxies. But what if dark matter is not perfectly cold? What if it is warm? Warm dark matter particles would move faster, and this motion would resist gravity on small scales. It would smooth out the small density fluctuations. This would mean that the first structures to form would not be tiny mini halos, but much larger, more massive halos, where galaxies would be born bigger, and the gas clouds at their centers would be bigger, potentially leading to the formation of more massive seeds from the get-go. Or consider another possibility: what if dark matter is not completely collisionless? We assume dark matter particles pass right through each other like ghosts, but what if they can interact with each other, even weakly? This is called self-interacting dark matter SIDM. In the standard CDM model, dark matter halos are predicted to have a very steep Cuspi density profile at their center. Observations of some galaxies, especially dwarf galaxies, suggest their cores are less dense, or cored. The SIDM provides a natural explanation for this. The interactions between dark matter particles would effectively heat the center of the halo and lower its density. However, these same interactions could also, under some conditions, lead to the core of the halo collapsing, a process called gravothermal catastrophe. This could create a very dense central region of dark matter, which would then act as a potent gravitational seed, accelerating the collapse of normal matter and the formation of a massive black hole. These are just two examples of how changing our assumptions about dark matter could alter the conditions for the first black hole seeds. The timing problem of supermassive black holes is one of the most significant challenges to the standard LCDM model on small galactic scales. It is possible that the solution is not a new piece of astrophysics, but a new piece of fundamental physics. It is a sign that there is something we do not understand about the nature of the dark universe. So while we search for the signatures of direct collapse or primordial black holes with our telescopes, particle physicists are searching for dark matter in deep underground labs. The two quests are intimately linked. A discovery in one field could completely revolutionize the other. The mystery of the giant black holes might ultimately be solved not by looking up at the sky, but by detecting a new particle here on Earth. Number 1, we are simply missing a piece of the puzzle. The simple truth is that we do not know. All the theories presented, from the standard to the exotic, have their own strengths and weaknesses. The laws of physics, as we currently understand them, are being pushed to their absolute limits in the extreme environments of the early universe. It is very possible that there is some new physical process, some unknown interaction, or some new type of object that we have not yet even imagined. That is the key to solving this problem. The formation of the first supermassive black holes remains one of the greatest unsolved mysteries in cosmology. After all of this, after exploring cosmic strings, dark stars, primordial black holes, and runaway collisions, we come to the most honest and perhaps the most important conclusion of all. We do not know the answer. Each of the theories we have discussed is a brilliant and creative attempt to solve a profound problem. Each is based on our best understanding of physics and cosmology, but each one has its own set of challenges, its own special requirements, its own lack of definitive proof. The light seed model is the most natural, but it requires impossibly fast growth. The heavy seed models, like direct collapse, solve the growth problem but require very specific, perhaps rare, environmental conditions. The more exotic ideas, like primordial black holes or cosmic strings, solve the problem elegantly but rely on physics that we have not yet discovered or confirmed. It is entirely possible that the correct answer is one of these ideas, or a combination of them. But it is also very possible that we are missing something fundamental. We are trying to understand events that happened over 13 billion years ago in environments far more extreme than anything we can create on Earth. We are peering back to the cosmic dawn, a time when the universe was just beginning to light up. Is it so surprising that our current knowledge might be incomplete? Perhaps there is a new aspect to how gravity behaves at very high densities. Perhaps there is an unknown property of matter in its pristine metal-free state. Perhaps the interplay between dark matter and normal matter is more complex than we imagine. The history of science is filled with moments like this. For a long time, the source of the sun's energy was a complete mystery. Lord Kelvin calculated that if it were burning coal, it could only last for a few thousand years. The answer, nuclear fusion, required the discovery of a whole new area of physics. The problem of supermassive black hole formation might be a similar situation. It might be a signpost pointing towards a new and undiscovered country in the landscape of physics. This is what makes the question so exciting. It is not just a matter of filling in the details of a known story. It is about discovering what the story even is. The tools we have now and the ones that are coming are pushing the boundaries of what we can see. The James Webb Space Telescope is giving us our first direct glimpses of the era where these black holes were born. Gravitational wave observatories like LIGO, Virgo, and the future LISA will let us listen to the universe and hear the mergers of these objects directly. Each new piece of data adds a clue. For now, the formation of supermassive black holes remains one of the biggest unsolved problems in astrophysics. It is a story with a beginning we cannot see, a middle that is a whirlwind of chaotic growth, and an end that sees them sitting as quiet gravitational anchors at the hearts of nearly every massive galaxy, including our own. The final chapter has not yet been written.